The recording. Okay, good morning, everyone. Thank you again for your time, for joining us. Please let me introduce myself. My name is Firman Bagjajuangsa. You can call me Firman, and I'll be the host for today's session. Before I start and let our speaker to start sharing, please let me share some opening slides regarding this event. Wait a minute. As you may know, this uh, today's session is called Kolam FTMD or Colloquium Akhir Minggu FTMD in Indonesian, or in English is FTMD Weekend Colloquium. So currently, I am the coordinator for research, innovation, and community services in Faculty of Mechanical and Aerospace Engineering, or FTMD in Indonesia. It is my pleasure to welcome you to our very first Kolam FTMD session today, which is actually a webinar series. And this is actually an initiative to enhance scientific culture within our faculty. And also, I hope it can provide the scientific discussion forum, not only for discussion about the current research topics, both in maybe Indonesia and also abroad, outside of Indonesia, but also to initiate the collaboration between the researcher from FTMD and also from another researcher from in both in domestic and international institutions. I know today is I would like to note that today is the last working day before the holiday of Idul Fitri, quite long holiday. So I really appreciate all your attendings to today's event. So this is actually the introduction about our series, and I hope this will mark the first series and more to come about many research topics, cutting edge research topics, not only in Indonesia but also in outside of Indonesia. And that's all, I think, the opening from me. And please allow me to introduce the speaker for today. We have the speaker, honor speaker from Tokyo Tech, Professor Tomohiro Nozaki, or I usually call him Sensei. So because he was my supervisor during master and doctoral degree studies in Japan back like 5 years, or around 5 years ago. After I graduated and returned back here to ITB, to FDMD, we have been initiating and doing some collaboration with Sensei, which started with I'm sending several student exchange during by YSEP Young Scientist and Engineering exchange program, and every year I send one exchange student to Tokyo Tech from final year student here under my supervision to Nozaki Sensei lab. And this year we have also started the collaboration by research funding, which later on maybe I will be allowed to invite Sensei come here to Bandung. Yes, Sensei. Yeah, okay. Today's topic, as you may see in the poster, is about beyond plasma, exploring methanation and turquoise hydrogen in energy sector, where I think Nozaki Sensei has been working on plasma for energy sector for almost, for many years, yeah. And I hope Nozaki Sensei can show us a broad field of mechanical engineering field, focusing not only the conventional field of mechanical engineering, but also in wider sector of energy, and give us the a few of sustainable energy solution that maybe can shape our future on renewable energy or sustainable energy. So I guess that's all. Some opening from me. We will have around 45 minutes of talk or lecture from Nozaki Sensei. And after that, we will have another maybe 30 minutes or so for a question and answer session. So without further ado, Sensei, please, the Zoom is yours.
Okay, thank you very much. So first I want to share my PPT.
Yes, please. Yeah, we can see your slide clearly, Sensei.
Okay. Oh, correct. Okay, thank you very much for the nice introduction. And also, it's my great pleasure to give a lecture today in front of my Indonesian colleagues. So I also would like to thank you, Firma, and everybody, all of them, to setting up this nice online lecture. So as Firma already introduced that today I'm going to talk about beyond the plasma. I mean, the use of renewable electricity to control chemical reactions, try to reduce the CO2 emission and maximizing the utilization of hydrogens. And Firma mentioned that my discipline is actually, so which means that when I was a student, I study a lot about heat and mass transport. So this is my discipline, but this is well established, and it is a little bit from different from the state of the cutting edge science and technology field. But in the meantime, still, the heat mass transfer is an important part of the technology and the science. So today, hopefully I will able to tell you how the cutting edge technology can be supported by the basic fundamentals like heat mass transport or maybe chemical engineering things. So before starting my talk, I would like to briefly introduce the overseas partnership between Tokyo Tech and the other universities. So this map shows that the green one shows the country that some university in the country have some relationship with the partnership with Tokyo Tech. And of course, we have a very strong partnership between Tokyo Tech and ITB. So this is just to highlight the university in Indonesia, like ITB and University Indonesia and University Gajah Mada. So we have three universities that have a partnership with Tokyo Tech. So one of the oldest one is ITB that started from 1988 June. So this slide shows that this program supporting the faculty exchange and the student exchange, and also some student exchange will be supported by the tuition waivers. So this means some students can stay in Tokyo Tech without paying waivers, and they will be officially supported for their study and also the daily life. So this is a very generous support, especially for the student. And there are many opportunities, but I'd like to highlight one program, which is called the YSEP program. So this stands for the Young Science and Engineering Researchers Program, so which is called the YSEP program. So especially for the student, if you're interested in, please scan this QR code, then you can check how to apply this YSEP program. Also, what is the deadline for the application, what kind of scholarship will be available. So all this information can be available from the Tokyo Tech website. So this is just the summary of the showing the friendship between my Indonesian fellows. So actually, this is started from the knowing the Philemon, who actually came to my lab as a master student and a PhD student. So this group photo shows that here is Philemon and the other Indonesian colleague from Lukman. So then, since then, we have strengthening our relationship, and also in 2019, so another Indonesian colleague at Dimas, he's now studying in Germany, I think, for PhD study. And also I had the master student, Laman, he's also from ITB. And last year we have a YSEP student, Pilar. He belonged to Philemon Lab, and he studied a lot about CO2 mitigation or CO2 capturing and CO2 fixation as cement materials. and this is just for entertainment. But he always stopped my lab, and then we are continue to our collaboration. All right, so now I'm going to start talk about this research topic. So the first maybe 20 minutes, I'd like to overview the carbon neutrality technology. So what it means, how we can solve this problem. And then later, I'd like to focus a little bit more on the fundamental studies, because fundamental study is always needed to make a deep insight into our research topics. So from maybe the cutting edge molecular level science and also large scale industrial applications. So this slide shows the overview of the carbon neutrality technology studies available from Japanese government, Ministry of Economy, Trade and Industry. So this kind of a kind of roadmap is always updated. So maybe last year they showed a different diagram, but this year the roadmap is a bit different. So we try to, not only Japan, but all over the world, we try to reduce CO2 emission while maintaining our, economy without decreasing its economic activity. So this map shows a lot of important technologies like renewable energy, ammonia, synthetic methane, the production of cement, the CO2 fixation, and also you have to use biomass, that technology, and CCS, and so on and so forth. But the most important keywords in this map is that the use of hydrogen and also carbon dioxide as a chemical feedstock and conversion of these materials into the fuel and some chemical commodity is that we have to use renewable energies as a low carbon footprint energy source. So to achieve this, there are many strategies, and especially our laboratory are focusing on the so-called power to chemical concept. This means that we are using renewable energy or electricity to combat chemical materials. This is also known as the electrification of chemical industries. So why it is called electrification? Because conversion of chemical materials is controlled by heat, adding heat or heating or cooling the materials, especially when we need high temperature. For example, the methane conversion. Methane is one of the stable molecules that we need a high temperature. The temperature is more than 800 degrees C or even higher. So which means we always use combustion that produce CO2. So that's why the hydrogen which is produced by methane pyrolysis is not really green because it produces CO2 during the hydrogen production. So people want to use low temperature heat, which may be available from the industry waste. But this is also another problem from the application point of view, because as the temperature decreases, heat flux decreases. But this means the productivity of the material can decrease, so that needs large reactors or the cost should increase. So this means even the high temperature, low temperature doesn't matter, but as long as we depend on heat, then we cannot achieve the process innovations. So this is the idea that how to use, so then we want to introduce electricity to combat materials. So actually electrification has a long history of industrial applications. So typical application is a heating technology using electricity, not combustion. For example, the resistive heating or microwave heating or induction heating has been used in the industry, heating the steels or heating or other materials. So, but recently, the people are more interested in non-thermal technology or non-heating technology using electricity. So one of the good examples is the electrochemical reaction or water splitting using renewable energy. And also CO2 splitting into carbon monoxide is also possible by electrochemical reaction. And also this review article highlights photochemical reaction. Photochemistry is not directly related to electricity, but as long as solar power is used, this is quite green. So that's why the photochemical reaction and the photocatalysis is also included in one of the important electrification technologies. But as you may know, that this technology is well established, and so therefore people were looking for or exploring new technology except heating and electrochemical or photochemical reaction. And one solution could be plasma technology. So for example, this technology mapping is obtained from these review articles, but actually they are not really the plasma researchers, but still they highlight different types of plasma reactors. So because the plasma is controlled by electricity, so these are very good compatible with the renewable energy, and they activate the molecules and they convert, for example, CO2 into methane. This is known as methanation. And then plasma actually accelerates the power to chemical concept. So this kind of new field of science and technology is called plasma catalysis, which is known as emerging type low carbon technology. So as I mentioned that plasma is combined with heterogeneous catalyst, and applying this technology to the CO2 conversion or methane conversion or ammonia synthesis or cleaning the gas. So, but you will see a lot of review articles since 2020 or maybe a little bit earlier. But the importance of a plasma is not only the use of renewable electricity, but also another importance that the plasma can actually promote chemical reaction at much lower temperatures than the thermal reactions. So this diagram shows it is so-called Arrhenius plot. The Arrhenius plot provides us important information about activation energy, about how much energy barrier exists to control chemical reaction. So this example shows reverse water gas shift reaction or CO2 reduction to CO using hydrogen. So this is endothermic reaction, and we need high temperature to this chemical reaction to occur. So in the case of thermal reaction, reaction rate is slow, but with plasma at the same temperature range, the reaction rate is much faster than thermal reaction, and the activation energy also smaller. Because of this, the plasma is considered as one of the important and emerging type low carbon technologies. And our laboratory has been working on this issue more than 10 years, and recently we got a very nice grant from the government and they accelerated this research. But before introducing more details, I'd like to overview the more energy issues except the plasma technologies. So recently, the CO2 methanation highlights very strong attentions. I'm sorry, very strong attention because CO2 can be regenerated as a methane. So this reaction is expressed like this, that CO2 plus 4 hydrogen produce methane and 2 water. So this reaction means that we need 4 molecules of hydrogen to convert 1 molecule of CO2 and waste about 50% of hydrogen as a water. So this reaction is known as methanation, but in the application point of view, we also have to think about the efficient use of methane at the power station, for example. And then after combustion, we produce CO2, and this CO2 must be reduced by hydrogen. We also have to think about water electrolysis using renewable energies. So if we think about the CO2 methanation, we always think about all the 3 equations at the same time. And adding all these 3 equations, you can realize this is actually net zero production of energy and the materials. Energy is not produced at all, and the CO2 is not produced but not mitigated at all. This is net zero production. So that's why some people are still skeptical about this technology, that the CO2 methanation is not really green. So another problem may be that if we assume the production of 1 kilowatt-hour electricity at the state-of-the-art gas turbine combined cycle, assuming this energy efficiency, then this CO2 can be reduced into methane with green hydrogen that electrolyzer consumes this amount of energy, assuming 90% of energy efficiency. So this indicates that overall methanation efficiency is about 40%. This can be calculated by 1 divided by 2.5. So this indicates that overall efficiency is not as high as of the hydropower system, that is about 70 and 85%. So this is very efficient. So nevertheless, so this is the reason that two reasons that many people still a bit skeptical about this technology. But in the meantime, many countries perform the global simulation to estimate that we have to introduce as much renewable energy as possible into the society to suppress the global temperature increase below 1.5 degrees C. So this kind of huge energy treatment is not easy, but it may be possible by the concept of CO2 methanation. So imagine that photocatalysis, the efficiency from the solar light to CO2 splitting, for example, is that energy efficiency is maybe less than 1% or maybe 1 or 2%. It's quite low, but still a lot of people pay attention to this technology. It may be green. So with the same concept that we don't look at only the efficiency. With 40% low, then meaningless. I don't think so. So actually we have to think about the more big overview of the process that efficiency may be low, but if this technology can convert a lot of renewable energy into chemical systems, then this is very important. And also I want to mention a little bit about the efficiency of this process, but this is not energy efficiency, but it is so-called exergy efficiency of the system, assuming that energy efficiency is 100%, but we are looking at availability of or quality of energies. So for example, the methanation means that electricity can be converted into methane, converted into hydrogen and then methane. But as you may know that the hydrogen is green, but it's one of the most low quality energy source. So its quality of energy is not as high as electricity. So simply converting from electricity to hydrogen with 100% energy efficiency, but you can see that about 20% of energy is lost through this process. And we lose additional exergy from hydrogen to methane. So therefore, overall exergy efficiency is less than 80%. So now this is the reason that the people are looking for a new reaction system that is so-called direct methanation from electricity to direct synthesis of methane. So in that case, the exergy loss is dramatically reduced. That can save this amount of exergy comparing to the existing technology. So that's why people are looking for a new catalytic system that enables direct conversion of CO2 to methane. But unfortunately, this reaction has not been realized yet. Well, let me say that it is possible, but efficiency is still quite low. So then we have to always think about not only the energy efficiency, but energy efficiency. So one of the important answer to maybe the approach to answer this question is that we need the new technology or new low carbon technologies that do not rely on green hydrogen. So which means that we can use renewable electricity directly converting CO2 to other materials. That is that could be the one solution, or that could be the alternative technology, the methanation. Right. So the one solution may be turquoise hydrogen. That is, the turquoise hydrogen is the methane pyrolysis into the solid carbon and hydrogen. So if we compare the energy difference between the green hydrogen and turquoise hydrogen, you can see that green hydrogen, we need this amount of energy to produce 1 mole of hydrogen. In the case of turquoise hydrogen, energy required to produce 1 mole of hydrogen is about 13% compared to green hydrogen. So energy requirement is quite low. And also it produces carbon black as a chemical feedstock. So this is the reason that not only the green hydrogen, but the pyrolysis of methane is highlighting keen attention from the abroad, from all over the world. And also this is only the stoichiometric reaction, but in a real system, but the energy requirement for the turquoise hydrogen is about 20 or 30% compared to the green hydrogen. And also, I want to highlight that not only the hydrogen that from the production of carbon black is also quite beneficial with this turquoise hydrogen, because currently we are using the oil furnace method to produce carbon black. So the oil furnace method is that carbon and hydrocarbon feedstock is partially burned in the furnace, and then it is quenched by injection of the water, something like that. So because this process needs combustion to provide high temperature heat that produce this amount of CO2 per 1 ton of carbon black. But if you use electricity for the pyrolysis of methane, the CO2 emission is about 1/10 compared to the oil furnace method. So imagine if you want to replace existing oil furnace method for the carbon production, then you can greatly decrease the CO2 emission. This is another benefit of the electrification of the chemical processes. To research in our laboratory, we are developing new technology for the fluidized beta plasma technology that decomposes CO into the carbon black. You will see that the vertical reactor is put into the furnace, and you have some catalyst here. And you can see that we can produce plasma in these catalytic systems. So this diagram shows that the CO flow rate from the up to about 11 hours, you will see that the CO conversion does not change or is not deteriorating, which means that the catalyst activity can be maintained at more than 10 hours. And after 11 hours, we can actually produce carbon black like this, that the reactor is almost filled with carbon black without the activation of catalyst. I will quickly show some movies that how the process works. So this is just for the demonstration for the presentation purpose. We have a plasma here. The gas is introduced from top to the bottom and released at this point and flowing upward. And we will see that some like smoky fluid here. That means actually carbon black is produced and blown off and 11 hours that are produced like this. But as I mentioned that this is fluidized bed, so it is always moving around here. So then with this amount of carbon black, we still can produce the plasma during the process. Another important issue is that we have to remove carbon black. You can see that we can increase the gas flow, that it can continuously eliminating carbon black from the reactor and collecting in these metallic chambers. And also we have some carbon residues here. This can be blown up from the gas flow from the side. Like this, and then we continue to produce carbon black. So catalyst is freely generated like this. With this process, we can continue to produce carbon black from the carbon monoxide, and the carbon monoxide is produced from CO2. Right. Then we did some kinetic studies and some material analysis. I will skip the details, but I just briefly mentioned that this kind of reaction is really complex, but it can be quite predictable by the thermodynamic analysis. This diagram shows the phase diagram of the ion as a catalyst, carbon, oxygen, hydrogen. This kind of calculation is easily performed because this is only the equilibrium calculation. So you can see that carbon deposition occurs when the temperature is more than 600 degrees C. And because carbon is produced from carbon monoxide. So as the temperature decreases, the chemical reaction is becoming slow. So this is a good reason that to combine catalyst and the plasma, because the plasma can promote catalyst reaction. This is also quantitatively estimated by Eileen Scott that activation energy for the plasma reaction is about half of the thermal reaction. So this means that the carbon black deposition is very slow without the plasma, but the same temperature with the plasma, then carbon production is greatly promoted. Then also we think about application of carbon black to the batteries. So because secondary battery is also important energy devices. And so this study is performed in collaboration with other colleagues in the domestic universities. So we produce these kind of carbon blacks, and then my colleague actually fabricating the lithium-ion batteries and check its charge and discharge capabilities. And its performance is compared with commercial carbon black, which is known as catching black. So catching black is the name of the carbon black, which is known as a highly active conductive carbon black. And you can see, check this name, that you can find a lot of research papers about electrochemical application that device performance greatly increased. So what we found is that our carbon black, actually the battery performance is better than the catching black, which means that our carbon black is maybe better than the best carbon black or the commercial one. The reason is quite simple, that the commercial carbon black is like a powder form. So, but our carbon black is like this filament or maybe the coil, nanocoil, and that increase the surface areas and also providing the better percolation pathways. The lithium ions and electron can be transported between active materials using the carbon black. So then we are now working on the carbon black production, the application to battery. Right. So also we are working on the methanation reaction and also CO2 conversion or methane reforming using the plasma catalytic technology. And then now recently a lot of domestic company are interested in the plasma related technology, and we have a lot of discussion. But at the end of the discussion, no matter what the application is, the conclusion is always the same. So we say, so what is the mechanism of the plasma catalysis? How plasma promotes chemical reaction? How we can optimize the process or reactor design? So to answer these questions, we always need mechanistic studies. So then we are doing a lot of effort to understand how the plasma or electricity can promote catalytic reaction without heating the system. So as I mentioned that this is now attracting attention, you will see a lot of review papers. So this diagram shows obtained from this review paper showing that the plasma and surface interaction is quite complex because we have ions, radicals, electrons, photons, and many things here. And its catalyst is already complex. But the plasma catalysis is even more complex. It's difficult to say something really specific. But in our laboratory, we try to split into the basic reaction mechanism, like the Lang methanation, E-linear, and the plasma gravity. So there are many different types of such reaction, but maybe these three reactions is the very basics of the surface reaction mechanism. For example, that in the Lang methanation may be the most common surface reaction pathway. So I'd like to briefly explain for those who may not be familiar with this kind of surface chemistry. So that the gas phase molecule is first captured or absorbed from the surface, and then some molecule can be break into radicals, and then surface reaction occurs to produce final product. So the key issue is that all the molecule is absorbed on the surface, and then some chemical reaction or surface reaction takes place. But in the E-linear, it's generally speaking that much faster than the Lang methanation route, because one of the two molecules can be captured on the surface, but the other molecule is directly interacting or reacting with surface chemistry, surface molecules. So then we don't have to think about absorption process here, then this reaction is very fast. This type of reaction is always common recently with perovskite type materials. The gas phase molecule react with the lattice oxygen that produce oxygen vacancies. The oxygen vacancy is actually problems for semiconductor application or devices because it can trap electrons and device performance decreases. But the situation is totally different for chemistry because defect is a highly active reaction site. The oxygen vacancy can remove the oxygen from CO2 or C. and the surface reaction is greatly promoted. So we focus on these three fundamental reaction paths and set up new some model reactions like methane dry reforming that can be explained by lung methanation route, and then we produce the lanthanum modified nickel aluminum catalyst or either rigid catalyst. So we use the palladium-2 gallium alloy catalyst and apply this to the CO2 reduction to carbon monoxide. And as I mentioned, that the carbon black production of carbon monoxide, actually we are using metal oxide catalyst. So then oxygen vacancy actually captures oxygen from the CO, and then that produce carbon black on the surface. And the fundamental study has been already published in each papers. But today, time is limited. I only explain the second application or either video reaction path. Maybe another 15 minutes, and maybe I need to skip some slides. But before going into the details, I briefly explain the plasma reactor design. This is also important subject of research. So some of the paper open access, so you can review or download freely from the journal homepage. So up to now, I said just a plasma, but what kind of plasma? So this is called a dielectric barrier discharge. So we have two metals and one glass here, and then discharge current is suppressed by this material, so that's why we can produce highly non-equilibrium plasmas. This technology is commonly used for industrial ozone generators. So because plasma is easily produced, we can combine many different types of reactors like catalyst pellets and also liquid surface, or in liquid plasma is also possible with this technology. So this is a schematic of our plasma catalyst reactors, and this is the images of how plasma is produced in the catalyst pellet. To characterize the reactions, we always need to carefully check the temperature of the catalyst that is performed by the calibrated thermal cameras. And also one want to mention the power source. This is also very important part of these experimental studies. So the power source is generally very expensive, but if you can find very cheap, inexpensive, and compact power source like for the ozone generators, the size is about maybe 12 centimeters and maybe 20 centimeters size. You can carry this by your hand, and then cost it maybe $500 or even less. And you can produce this kind of plasma very easily. So this is very important part of these research studies, because we don't have to make a big investment to perform the experiment. Okay, so let me skip this. And then actually we are studying how plasma interacts with surface, but there are the big questions for this kind of research studies, because we are using catalysts with polar structures, and the gas molecules always interact with these micropores. But the question is how the plasma interact with micropores, or the plasma do not interact with micropores. So this is a very important question. But answer is actually plasma is so reactive that all chemical species can complete a chemical reaction before diffuse into micropores. So this can be explained by so-called Debye length that limits the plasma diffusion process, and also Paschen's law. So it means that gas breakdown doesn't occur in the micropores. So if you're really interested in the plasma chemistry, you can check Debye length, Paschen's law, that you can further study so what it means. So this is also confirmed by the experiment that the catalyst pellet, like 3 millimeters, is exposed to the CO2 plasma. So for the thermal case, the reaction is not occurs here. I'm sorry. But with the plasma irradiation, that you can observe the color change. So kind of whitish material shows the nickel oxide. This is possible only 20 micrometer depth. So this means that the plasma interaction occurs only on the surface of about 20 micrometer thickness, but inside cavity there's no plasma interaction. So to overcome these drawbacks of plasma catalyst interactions, we developed fluidized bed plasma reactor like this. You can see that the powder is fluidized in the vertical reactors while we can generate plasma here. But also the powder, the surface area increases that it can strengthen interaction areas between plasma and catalyst. And also, as you may know, that fluidized bed is good for promoting heat mass transport. Okay, it's really difficult to characterize these complex behaviors, but there is the well-known chart for the fluidization to explain fluidization behaviors. So this is called the Gerdato chart that is published in 1973. This is still provided as very important criteria for the fluidization that can be divided into four different groups, like group A, this is cohesive, this is irritable. This means that we have a uniform fluidization. The sunlight means that we have like a bubble fluidization or turbulent fluidization. And also spottable fluidization means that powders is blown off by the gas flow. This is frequently used for like a chemical industry, make a thin coating for the medicine or things like that. So just briefly shows the video. Well, okay, so we have a uniform fluidization in this case, but if not, you will see that when the plasma is on, the particle is charged by electron ions, they all stick to the wall. And the plasma off, you will see very strong fluidization. But during the plasma on, they all stick to the wall. We solve this problem, but how to do it is simply increase the mean size of the particle, and then we can solve this problem like this. So this is explained based on the Gerdato chart. Okay. So then we're using a special catalyst that is palladium to gallium, the unique catalyst. Just to repeat that we have a 5 nanometer mean size catalyst, and the palladium and gallium is well overlapped, and this shows very nice crystalline structures. The whole bunch of the material characterization confirms that we have very nice palladium to gallium catalyst. And then we're using this catalyst for the fluidization here. And then the left-hand side shows that this diagram shows the CO2 conversion with catalyst temperature. The catalyst temperature was measured by thermography. So for the red one is the thermal reaction without the plasma. So the conversion is increased by increasing catalyst loading. So this is generally observed without. But what is interesting is that when the plasma is superimposed like this, and then CO2 conversion is doubled. And when the operating frequency is 100 kHz and catalyst loading is 10%, CO2 conversion reaches about 60%. That is almost doubled compared to thermal reaction. And what is even more interesting is that CO2 conversion is more than thermal equilibrium. So this is quite interesting because catalyst is controlled by the thermodynamics. So it is always difficult to overcome thermal equilibrium like this. But in this particular case, we confirmed that CO2 conversion is not limited by thermodynamics. Then we need to answer why this happens. And then we did a whole bunch of characterization and quantum chemistry calculations. So as I mentioned that from the observations, activation energy decreases. But key radical species is actually the vibrationally excited CO2. And this energy, activation energy is only 80 kilojoules per mole. It's a very small amount of energy. But what observed that the drastic decrease of activation energy that decreased from 75 to 44, about 31 kilojoules per mole. But this is possible by only 80 kilojoules per mole activations. But this is well explained by the molecular beam study and also quantum chemistry calculations. So molecular beam study shows that when CO2 is generally linear structure, simply because it's energetically stable. But if electron impact can create bending mode CO2 like this, what happens is that energy level decreases or its LUMO level decreases. So this means that the linear CO2 is very stable, but the bending CO2 is quite reactive, and they can easily react with some other chemicals, something like the hydrogen, which is absorbed on the metal surface. And as I mentioned, that the Lumo level decreases, this means that the CO2 is now looking for the electrons. And then the hydrogen is negatively charged on the metal. So then the direct interaction is promoted. This kind of reaction scheme is confounded by the quantum chemistry calculations. Actually, this is very difficult, but some specialists like Professor Morikawa has a long history of doing this, and they confirm that activation energy can decrease when the CO2 is in the bending mode. And the question is that this is already confirmed more than 20 years ago by the fundamental study. But all these experiments is conducted in the cryogenic temperature, minus 200 degrees C, and the super vacuum condition, like 10 to the minus 6 Pascal. So then it is interesting from science, but no way to the industrial applications. So then we are providing the plasma technology that we can produce plasma at ambient conditions, and we can produce a lot of bending mode CO2, and indeed confirmed the drastic promotion of a chemical reaction. At this point, I want to mention that most important thing, the role of a plasma is to activate molecules, and then molecular orbital must change because of this activation. The CO2 is also has a different types of vibration, like stretching mode or anti-stretching mode. In that case, the molecular orbital doesn't change. So we may observe slight decrease of activation energy because molecule is activated. The same principle may be applicable to diatomic molecules, because diatomic molecules only have stretching mode, not bending mode. So this means if the diatomic molecules is excited into some level of the vibrational state, then some small amount of activation energy may be observed. So this is confirmed in our laboratory for the methane activation, that we also observe a drastic decrease of activation energy because methane is in the stretching mode vibration, and then its molecular orbital changes, and also CO2. In the case of nitrogen, the activation energy is basically not decreased, but nitrogen is activated into the vibrational level, and then relatively amount of activation energy may be decreased depending on how much nitrogen is activated into higher vibrational levels. So even though we are using the same plasma, but depending on the molecules, the plasma reaction promotion effect or mechanism is totally different. We need to understand this. And then maybe time is approaching to end, maybe 45 minutes. But I want to quickly overview our recent study that we recently set up the in situ transmission infrared spectroscopy to identify the surface chemistries. So we have FTIR plus cell here. So, and then we can generate a plasma like this. And the plasma produce activated species that interact with plasma and catalyst here. Then we can identify what kind of subspecies to produce on the surface. So this is very easy spectral change depending on time. So first 8 minutes is only thermal reaction, and then another 8 minutes we have plasma reaction, and then plasma is turned off at this point, and then again thermal reactions. So this measurement was performed at 250 degrees C, because at this temperature range, no reaction occurs by thermal reaction, but we have a drastic increase of CO2 conversion at 250 by plasma. As you can see here, that for the first 8 minutes, no peak appears. This means that the chemical reaction or CO2 reduction is not appearing, does not occur. But as soon as the plasma is on, the CO2 absorption peak increases like this because CO2 is activated into maybe the bending mode vibration. And when the CO2 at the plasma is off, that all reaction is decreases like this. And we further confirmed this experiment with a different condition in the confirmed that important intermediate species is monodentate formate species. HCOO means the formate species. So that appears in these areas. And then So in this case, CO2, hydrogen CO2 is introduced intermittently. And during the first 6 minutes, there's no CO2 and no peak appears. And at this point, we are switching the gas from hydrogen to CO2. At this moment, CO is produced, but decreases because lack of hydrogen. Then it produces intermediate species. And all these experiments is conducted with the plasma, and we found that we produce intermediate species, but no CO peak appears. This means that the rate determining step is the decomposition of monodentate formate. So this reaction is not promoted at all with the plasma, therefore no CO peak doesn't appear. In other words, we observe CO peak appears because this decomposition process is promoted by plasma. So we are actually identifying the rate determining step combined with the aluminum spot experiment. And we further performed the quantum chemistry model, and I just briefly explain this simulation that we have actually two rate determining step. That is the formation of monodentate formate. There is a big energy barrier to overcome. So this can be decreased by two reasons. One is that we're using alloy catalyst that can decrease the activation energy from 110 to 68, but it further decreased from 68 to 44 because CO2 is in the bending mode. Another activation barrier, important activation barrier, is the decomposition of this species into the formula. So by looking at energy barrier for this reaction, it's a 72 or 74, depending on the palladium or palladium 2 gallium ion. But this reaction is not promoted by the catalyst alone. Then we need another strategy, that is the plasma, that can decrease from 74 to 44. In overall, that these two reaction paths is promoted by plasma. That is that we found the how plasma can promote overall reactions. And let's skip this one. All right, so then maybe this is the end of my talk. I'd like to briefly thank you our acknowledgement funding source. And each experiment is performed by not only students, but collaborators like other professors in Hokkaido University, and also plasma diagnostics. And also I'd like to thank maybe a special thanks to our PhD students, they all international. And now we are applying these basic findings to the CO2 methanation and the other chemical reaction process. All right. Thank you very much for your kind attention. I'm happy to answer any question you may have.
Yeah, thank you very much, Sensei, for your explanation and quite deep, I think, regarding the plasma and quite chemical surface chemistry, for example. I hope everyone can see and understand about the development of plasma and its use for energy sector. I would like to open any question from the audience. If there are any, I can see there are two questions, Sensei, in the chat box. If there is no,
I'm now leading.
Yeah. First, I would like to offer, is there anyone that would like to ask directly to Nozaki Sensei? If no, oh yeah, I think we have one, and after that, maybe we can read the chat, Sensei. Yeah,
Okay.
Fariski, this is our bachelor student, Sensei.
Okay.
Yeah, Pak Firman. I have a questions. So you mentioned about the methanation process before, but I don't quite yet understand about why is it beneficial for us to do the methanation process. So what I infer is that we need CO2 to produce the methane in methanation process.
Yes.
But as we know, CO2 concentration in the atmosphere is very low. So it takes a lot of energy to capture the CO2 itself. So I don't quite yet understand about why is it beneficial to do this methanation process.
Okay, so yeah, thank you for the question. It's a very important question. So maybe you are thinking the CO2 capture in the atmosphere, right?
Yeah.
Is this correct?
Yes.
Okay, so in the atmosphere, we have about 400 ppm CO2. So as you mentioned, this is a very inefficient and maybe very expensive to capture CO2 from the open air. So, but in this particular case, not only me, but many people are thinking about CO2 capture from the gas turbine or power stations. And in that case, CO2 concentration in the flue gas is about 20%. So it's still not easy, but it's much more efficient than CO2 capturing from the open atmosphere. So then this is explained here. So for example, if you're really interested in the CO2 capturing with air, we may be needed direct air capture like this. This is also a lot of debating about this technology, efficiency and cost. But one possibility is capturing the CO2 and injecting into the ground and to fix the CO2 as minerals. This is one solution. But if we want to regenerate the CO2 as methane, we can use it at a power station and collect the CO2 and convert it into methane. So we have, I'm not saying that CO2 methanation is always good, but it depends on CO2 capturing, transport, and storage technology too.
Yeah.
Did it answer to your question?
Pak Rizky?
Yes, Prof.
Yeah, maybe I can confirm that, Sensei, maybe this synthetic methane is a form of reutilization of CO2 that have been captured previously from maybe power station flue gas, for example, so that we
Yes.
can defer or delay the emission of CO2, that we can use it once again to produce the methane that can be used for the current technology that I think utilizing methane, I think it's quite widely available compared to if we using hydrogen as hydrogen, because the combustion or the utilization of hydrogen as a fuel may be quite more difficult than the methane. Yeah, Sensei.
Yeah. Although also CO2 must be recycled many times. If not, eventually CO2 is released into the atmosphere.
Yeah.
So in that case, this technology is not really green. This is another reason that some people are skeptical about this technology, that this is not really green.
Yeah. Okay, Sensei, let's continue with the next question from Pak Putro. He is one of the lecturer also here. If I may miss it, could you please elaborate the use of carbon black in the combustion process? What is it for? Thank you.
So what does it mean?
Yeah, the carbon black, he thought that you use the carbon black for the combustion,
Yeah.
or you make it through combustion, partial combustion.
Okay, so so this is a kind of established technologies. The carbon black is produced from, for example, some oil is hydrocarbons that is decomposed into carbon black. But to do so, we need high temperature. You have to produce high temperature, that is oil is partially burned like this. Then this high temperature is mixed with feedstock. And then, for example, oil is decomposed in carbon black. This is the oxygen black combustion process. Maybe you have some experience that you produce a lot of soot, maybe the same principle. So because of combustion here, it produces a lot of CO2, about this amount of CO2 per 1 ton of carbon black. So a lot of people know that this is not really green, but this is currently, mostly accepted technology that we need to look for some alternative technology. One possibility is like methane pyrolysis, using plasma or using electricity heating system, not combustion.
Okay. Pak Putro, are you listening, or you have any further clarification maybe? Okay, I guess, yeah, he's enough with that. And then the next question, Sensei, from TBS Energy Utama. This is actually Lukman. Lukman contacted me. I informed
Okay.
him about this webinar, and then he asked one question. But unfortunately, he cannot stay here. I think he left
Mhm.
already. He has two questions. While doing the mass production of turquoise hydrogen, can we continually reuse the catalyst to minimize the operational cost? And in your professional judgment, what is the minimum scale of hydrogen production per year to make this concept economically viable?
Okay, this is also an important question. I said that the turquoise hydrogen is that well, it's maybe better that I have on the slide. Maybe I don't. Okay, so for example, the methane pyrolysis attract keen attention. So one technology is something like this that is proposed by Karlsruhe University in Germany. And also another technology is a zero carbon company named Zero Carbon. UC Santa Barbara has developed. They are using molten metal, liquid phase metal. Methane is introduced, and then it decomposes carbon black hydrogen. The principle is the same as turquoise hydrogen. But the problem of this technology is that temperature is more than 1000 degrees C. So because of high temperature, the reactor always contaminated by carbon black. It is finally clogged, and then we need frequent maintenance. So in that case, maybe to answer your questions, the catalyst is very quickly deactivated, maybe within maybe a couple of hours, I don't know. But this is a big problem to solve. But as I mentioned today, my technology is operated at 600 degrees C, and the reactor is nicely regenerated, no clogging, no carbon deposition on the wall. Simply increasing the gas flow, then all the carbon black is blown off. So therefore, I think that we don't have such a problem like these high temperature processes. So therefore, to my answer, up to 10 or maybe 20 hours of operation, the carbon catalyst is not deactivated at all.
Oh.
So this is the benefit of using a plasma, that activation of reaction at a low temperature. We don't need high temperature at all. And the second question is about economy, right?
Yeah.
So actually methanation is, we need to process huge amount of CO2. But this is not compatible with renewable energy because renewable energy is small scale. So we always have some need to look for some compromise that a large scale power production produces huge amount of CO2 that must be converted into methane using small scale renewable energy. So then actually we don't have a good answer for this problem. So then we are proposing plasma technology that can be very compatible with small scale renewable energy. And on and off is very easy. So actually, I didn't do any economic analysis by now, but I would propose like plasma technology is compatible with, for example, biogas power system. So this means that 100 kilowatt power is generated by gas engine that can be operated or enhanced by plasma reactor. Or if you think about, for example, 1 megawatt wind power, just one wind power to produce 1 megawatt renewable energy that can be combined nicely with plasma. But imagine that 1 megawatt wind power cannot compatible with 1 gigawatt thermal power plant, right?
Yeah.
So then if we think about the plasma technologies, maybe up to 1 megawatt, this is quite challenging though, but up to 1 megawatt, maybe between 100 kilowatt to 1 megawatt power output energy device, maybe could be one solution for the plasma application.
Yeah. Okay, Sensei. before maybe I see several, I think most of the attendants here is
Mhm.
I think bachelor students and so on behalf of the students, maybe I would like to ask very general questions and say regarding the hydrogen. As you may know,
Okay.
hydrogen is quite hype currently in Indonesia. Even our electrical company started to build hydrogen refueling station
Mhm.
for car here in Indonesia, and also we start to build our national standard for hydrogen. So you see, our government also see that hydrogen is one of the I don't know, maybe the hope or the potential to accelerate the renewable energy and clean power generation and so on. But
Mhm.
I would like to ask you about your opinion. How do you see the role of hydrogen in the energy chain? Yeah, because based on your explanation that hydrogen have to be produced at least by green technology, for example, and is it really suitable if we use hydrogen as energy storage or energy transport or energy carrier between island, for example? In what
Mhm.
way, in what kind of scenario the hydrogen will be suitable, including this kind of methanation technology in maybe the future energy system in maybe yeah in Japan or maybe later on in Indonesia, Sensei, in your opinion?
Okay, so maybe I think, for example, between in the case of Japan, in the case of Indonesia, the situation is totally different. So, for example, in Japan, we don't have natural resource.
Mm.
Then, at the moment, I don't know this is the final answer or not, but at the moment, Japan's government try to import liquid hydrogen,
Yeah,
which is produced in the Australia
yeah,
from the brown coal,
yeah,
right? And then after that, the Australia had CO2, but they can do CCS.
yeah.
So they have a huge amount of unavailable coal, low coal, cheap coal, but they produce expensive hydrogen, so they can make a big business. And then Japan's maybe only way is to import hydrogen. The problem is that in Japan, we don't have so many fuel cell cars.
Mhm.
We have too much hydrogen, but no way to use it. So this is another problem. We always have consumption, production is always maybe the same. Otherwise, storage of hydrogen is very expensive.
Mm.
So that's why another reason recently, Japan or Kawasaki heavy industry has developed hydrogen combustion gas turbine system for the power station. So otherwise, we have a lot of hydrogen incoming from Australia, but no way to use it. So then we always have to seriously think about import and use of hydrogen.
Mm.
But in the case of Indonesia, I think maybe situation is different because you are one of the biggest coal exporter, right?
Yeah, and
You
that's
can also have the potential to produce hydrogen from coal.
mm,
And also Indonesia consists of many different small islands.
yeah,
You need to promote energy transfer from islands to another island, right?
correct.
So then this kind of energy production, storage, transport scenario is totally different from Japan, Indonesia. So maybe you can run something from Japan's technology, but also you need to develop your own technology, which is compatible with Indonesia, right?
Yeah, yeah.
So then maybe I think use of coal and methanation
Mm.
to transport the storage is much cheaper than hydrogen.
Yeah.
So then I think you can more interested in destination rather than hydrogen itself. But this is my opinion. I didn't do any economic analysis yet.
Yeah, yeah, yeah. Yeah, and also by producing methane, you can still using the current or the existing technology for power generation, essentially, because maybe Kawasaki or maybe MHI and other
Mhm.
manufacturer for gas turbine, I see them quite difficult to develop and cost quite highly on developing the hydrogen burner because it has quite a different characteristic on combustion with the methane, but producing methane, maybe you can use the current or existing gas turbine, for example. Yes.
Mhm. Yeah, but you know, after combustion, I'm sorry, hydrogen turbine.
Mm,
After combustion, we don't have CO2, right?
yeah,
That is great. But
yes,
after combustion, we have a heat.
yeah,
And heat from hydrogen combustion or heat from coal combustion doesn't matter, right?
yeah,
So heat is heat. So that's why the efficiency of the power plant from natural gas and the hydrogen is basically the same. This
yeah,
is maybe another problem.
yeah.
So we have to pay additional cost for hydrogen.
Yes, correct, Sensei, to produce.
Our electricity cost increase.
Yeah, yeah.
Yeah.
That will be, yeah, cleaner technology will cost you more on electricity, isn't it?
Yeah. If you are ready to pay money, no problem. But if you don't,
Correct. That's
I don't think that hydrogen is a solution.
yeah, yeah, yeah. Okay, okay. Is there any question again from the
Maybe
audience?
I can see one question in chat, but unfortunately I can't read Indonesian language.
Uh,
This is one question.
I'm sorry, Sensei. This is not question. This is my offering to
Okay.
everyone. If there are any question that you can just write down.
Terima kasih.
Yeah, terima kasih.
Okay.
Terima kasih is thank you. This is for attendance list, Sensei. There is the attendance list. Yeah. Yeah, so student that come may fills the attendance list.
Mhm.
Oh, yeah. I have another additional question, Sensei, about the plasma. Maybe not many of students of particularly from our faculty, mechanical and aerospace engineering, regarding the plasma. How good is the plasma if we would like to scale it up to industrial scale? Is there any, like, for example of pilot project? Maybe you have been done doing the plasma experimental for many years, but how about the scalability and on larger plant, say for example?
Okay. So for the thermal plasma, it's like a welding,
Yeah,
right?
yeah.
Thermal plasma is that there is a huge scale. Like for example, the turquoise hydrogen is operated by the company which is called the Monolith.
Oh,
This is a company. They produce hydrogen this amount because thermal plasma is very energy intense. That they can process the hundreds of thousands of gas flow rate.
mm,
So the problem is this is also high temperature. Then process is frequently stopped and cleaned. Otherwise, carbon black clogs the piping and then everything stops. But otherwise, in terms of scaling up issues, that monolith technology is quite good. But we are working on low temperature plasma. So in that case, this kind of mass treatment is not possible.
mm,
So maybe, for example, one reactor can treat like 10,000 liters per minute gas, for example. And we can optimize it, and maybe we can use maybe say 10 or 100 of reactors in parallel.
okay.
This is one approach to solve scaling up issue. And then here is, I'm sorry, this is not O2, but this is ozone generator. The
Oh,
industry scale ozone generator, you will see a lot of small reactors in
mm,
parallel. And then large scale ozone production is possible by plasma reactors. So this is maybe 100 kilowatts power consumption. Then up to that level, we can scaling up the gas treatment with the plasma technology.
so yeah, as you mentioned, maybe the plasma technology may be suitable for the small, maybe relatively small scale renewable energy coupling with this technology compared with the large scale thermal power plant, for example. So you can like a bridge between the small scale renewable energy and to produce the hydrogen, and then doing the methanation to maybe bridging those methane to the larger power generation plant, essentially.
Yeah, that's correct. So for example, the power station is it's okay that is supported by some kind of government support, and also steel making company. They are also independent private company, but they always have some kind of government interference. They're supported by the financially. But if you think about like small industry, like only 10 people work there, but still producing CO2.
Yeah.
For so many small scale industry, then government may ask, okay, individual industry must reduce CO2 10%, but they don't need large scale process technology, but they need small but cheap technology, right?
Yeah.
And then plasma technology combined with renewable energy may be the solution that can reduce CO2 in a small scale industry. But in total, like solar panel on your rooftop, right?
Yeah.
Solar panel is small, but number is great. Then total impact may be, I think, beneficial.
Oh, yeah.
So not only just a single reactor, big or small is not an issue, but how many small reactor can be supplied in an inexpensive way.
Yeah, Sensei, I'm sorry that, but I have another question, Sensei.
Okay, no problem. Yeah.
I want to allow everyone, but I still curious about this technology of plasma regarding the variability or the intermittency of the renewable energy. As we know that maybe solar panel or maybe wind turbine in residential area has quite up and down in electricity supply. So does it affect the effectivity of this plasma technology, or the efficiency will drop as for example, the electricity is not that stable, for example?
Well, I think anyway, so plasma is anyways it's easy to operate. And so this is so that's why I showed some device like this.
Yeah.
So this plasma is just on and off. It's quite easy. So if the renewable electricity is supplied, we just simply turn on plasma and do some chemical reaction. And if the wind stops, we just turn off the plasma reaction, no problem. The problem may be the temperature control. If the temperature suddenly increase, the glass breaks, right?
Yeah.
And also temperature increase is not as quick as the plasma generations. So if we want to heat up the system from the 100 degrees C to 200 degrees C in 1 minute in a large scale is not possible.
Yeah.
But I want to remind you that we don't need such high temperature. Temperature difference is very small, but plasma on and off is very easy. So that is another reason that plasma, not only plasma, but electrochemical reaction is a very good compatibility with variable renewable energy source.
Yes, correct. So we can use this technology as energy storage as well, essentially, yeah, to maybe replace a battery, for example, the electrochemical battery.
Yeah, I think so too. Yeah, but battery is not really cheap, right? So the best solution, for example, is that we can produce methane, and then this methane is introduced into the pipeline.
Oh, okay.
And then if the wind stops, plasma stops, and gas injection also stops, no problem, right?
Yeah.
But however, there's a lot of regulations. If you want to inject the gas into the existing pipelines, that you have to carefully control the gas component. And then this is a negative side of Japan. For example, we import liquid natural gas, right?
Yeah, from Indonesia.
So this means that natural gas methane concentration is very high. It's very purity high. So then all infrastructure is developed assuming that we are using high purity methane. So gas company never allows impurities. The situation in the European country is different. They are mostly using a pipeline, right? So all infrastructure is designed so that methane content is changing in a large degree. So they are quite flexible in terms of impurities. And this is a big difference between different countries.
Yeah. Currently, we don't have also, we have only small part of gaseous pipelines in the city, but not as that big, in Japan or in Europe.
Otherwise, we have to compress the gas. We need the gas holders. We need the transportation trucks, right? That is expensive.
Yeah. Oh, okay. I'm sorry to keep everyone waiting. Is there any question from any other audience or students? Okay. Sensei, I guess we only have several minutes left in this meeting. I know you are also busy and have another agenda after this. You have to go out. I will not hold you any longer. Sensei, thank you very much for
Okay.
your sharing. I hope
I'd like to thank you for your
our
invitation.
collaboration. Yeah. It's my pleasure, Sensei. I hope our collaboration will continue, and I
Yes.
guess I really hope that I can invite you later on to Bandung to maybe give
Okay,
some
yes,
another talks and
I'm willing to visit Indonesia.
lecture. Yeah. Thank you. Before we end this meeting, Sensei, can we take a picture of everyone
Sure.
else?
Yeah.
Thank you
Great.
for turn on your. Everyone can who are available may turn on your computer or camera. Thank you, Pak Prihadi, Pak Indrawanto, Pak Bentang, and any other. Let me take a picture first. Wait a minute.
So is my camera on?
Yeah. Camera clear, really clear, and handsome.
Okay.
Oh, another time, Sensei. Wait a minute. Wait. Okay. Wow, someone is right on a bus, maybe going back to the hometown because this is last day of lecture. Okay, Sensei, I took the picture. I will send you. And also, Nozaki Sensei, if you don't mind, we get your slides later on? Maybe you can send me email and I will maybe.
Sure. Yeah, I will.
Yeah. I think that's all from me. Thank you, Sensei, for the first session for Kolam FTMD, our regular colloquium session in our faculty.
Sure.
I hope you are fine there. If you have any last word, for example, you please go ahead, Sensei.
Me?
Yeah, maybe you have some
Okay.
words. Maybe
Well,
last.
I hopefully I
Very good.
will visit ITB and then recruit more good students in Tokyo Tech. I'd also like to send our good students to Indonesia. So because we have a long history of the partnership between ITB and Tokyo Tech, I really want to continue this relationship. And I'm very happy to serve this kind of activity. And also welcome back, Peterman, to Tokyo Tech.
Yeah, thank you, Sensei. See you later. Okay, Sensei, and for all audience, thank you for your time and see you on the next Kolam FTMD session. Take care and Assalamualaikum warahmatullahi
Have a good day.
wabarakatuh. Thank you, Sensei. Have a good day. Thank you. 失礼します。
じゃあ、フィロン、僕も出ますね。
はい、ありがとうございます。
はい、じゃあ、東京で会えるの待ってます。
はい、またお願いします。
はい、じゃあ